So this is a lecture on chapter 13, which is chemical kinetics. We're going to start with a little history. In 1850, Ludwig Wilhelmi measured how fast sucrose basically reacted with acid to make glucose and fructose. And he was able to show that the rate of how quickly it was reacted depended upon the initial amount of sugar present. The more sugar you had at the beginning, the greater the rate of the reaction would be, which is what chemical kinetics is. Chemical kinetics, remember kinetic or kinesiology is movement, which is basically the rate at which a chemical reaction proceeds. So it's how fast reactants are turned to products. It's a quantity that reacts per unit of time. Usually that quantity is given in molarity. If we have a slow rate, that means there's only a small fraction of molecules that are turning or reacting per period of time, and at a fast rate, there's a large fraction of molecules. There's a couple different ways we're going to write what we call rate expressions. The general idea, the general way to calculate is shown here. So we have an equation, and we're going to say that the rate of H2 is negative of the concentration of H2 over the change in time. So if we look at these brackets, that means concentration, and when we talk about the change in concentration, we mean the final minus the initial for both things. You can do the same thing for the second reactant I, and then the same thing for the product HI. But if you notice with the product one, it's 1 over 2. So you're going to do 1 over the coefficient. So you see the coefficient here is 2, so it's 1 over 2. And notice that that one is positive. The reason that one is positive is because during this reaction, at the beginning, you have this reactant and this reactant, which are slowly turning into products. So you're going to have the two reactants steadily decreasing in concentration, which is these minuses here, and you're going to have the product steadily increasing, which is why there's a plus sign. Reactant concentration, that's what these little brackets show, decreases with time because they're being consumed, and the product concentration increases because it's being formed. You must consider the coefficients of the balanced equation, the stoic of it, and I just showed you where those coefficients come into play. You can look at a graph of change in concentration over time to get something called the instantaneous rate. If you look at the word instantaneous, it has the word instant in it, which is like right this instant at this exact point in time. And the way you calculate that is simply by taking the slope. So if we look at this graph, we have concentration of reactants here is the red line and product is the blue line over time. And you see the reactant concentration is going to decrease, the product concentration is going to increase. And what's going to happen is these are going to turn into straight lines of steady concentration. Notice that the increase and decrease is not linear. It's not, decreasing by an interval of 2. It's actually an exponential increase and decrease. So when you do the instantaneous rate, it's going to be different than the average rate of the whole reaction. And the way you do instantaneous is you take the tangent of the line here, the slope of the tangent line. So there's 3 different ways of measuring the rate. The initial rate is the beginning. At time 0, on this graph that we're looking at here, it'll be right here at the top. The instantaneous rate is at any point along the graph. Remember, the instantaneous rate is going to be different depending on where you're looking because it's not a linear decrease. And the average rate is exactly what it sounds like, the appearance of product or disappearance of reactant over the average. Equilibrium occurs when the reactants and products are moving at equal rates. Equilibrium is next chapter. We are not studying it here. We're going to start borrowing some ideas from equilibrium. To get the instantaneous rate of reaction or the rate at any given point, you're going to use the equation shown here. We showed that at the beginning. So it's for reactants, remember, it's going to be negative. For products, it's going to be positive. You do 1 over the coefficient, and then the change in concentration of the substance over the change in time. Couple factors that affect reaction rates: concentration. The key words here are going to be number of collisions, because in order for something to react, it must collide with one another. Things will not react if they do not collide. So one thing is the concentration of reactants. The more collisions there are, the more the rate will be increased. Temperature is a measure of how fast the particles are moving. So the more kinetic energy means you have more collisions, or the more molecules with required activation energy form products. The physical state, so if we have things at the same state of matter, like gases or liquids or solids, those are always going to react more quickly than things that are 2 different states. And finally, a presence of a catalyst. A catalyst works by lowering the activation energy. We're going to see that on a graph soon. A rate law is just an expression of rate. You can see it here. K is the rate constant. That is something that has to be given or calculated for. It's going to be different for every reaction. N is the reaction order, and A is going to be the concentration of reactant A. There are two types of rate laws. There's the differential rate law and the integrated rate law. The one that we're going to use most often is the differential. We just kind of call that rate law. So if you see a problem where it says rate law, it means differential. Integrated, it's going to specify that it's integrated rate law. Differential is a rate as a function of concentration, and integrated is the concentration of the species as a function of time. So there's three main reaction orders. There's zero order, first order, second order. So if we go back real quick to the rate law, that's what goes here as the exponent. So if it is zero order, n equals 0, and this is when the rate is independent of the concentration. The rate of the reaction is not dependent on how much reactant there is. For a first order, n equals 1, and the rate is directly proportional to the concentration. So that means if the concentration's doubled, the rate's doubled, and so on. Second order is n equals 2, and this means the rate is proportional to the concentration, which means if the concentration's doubled, the rate will be will be quadrupled, times 4. So there's a couple of general graphs for each order. Now remember, differential is the one we're most often going to see. Integrated is the one that's going to specify. The key difference between these graphs is the y and x axis. Differential is going to be rate over concentration. Integrated is going to be concentration over time. So that's really what you have to look at to tell which type of graph you have. For the differential zero order, you're going to have a straight line. Because remember, for zero order, the rate does not depend on the concentration. For integrated, you're going to have a negative sloping line. These equations will come into play. You may need them to calculate things, so make sure you're paying attention to them. Again, a zero order reaction is independent of the concentration. The rate does not slow down depending on how much reactant you have. The half-life equations here, half-life is the time it takes for half of the substance to turn into products. It's exactly what it sounds like, half the time it's needed. For first order, again, notice the x and y axes. For differential, it's going to be an upward line. For integrated, it's going to be downward exponential line, slope. So if you double the concentration, the rate will increase by the same factor. So if you double it, it's going to be doubled, etc., and so forth. The rate slows down as the reaction proceeds because the concentration of the reactant slows down. And here you can see the half-life equation. For second order, you're going to have an upward slope for differential and a downward exponential curve for integrated. This is where the rate increases by a factor. So if you double the concentration, the rate's actually going to be increased by a factor of 4. The rate flattens out more quickly because the reactants are used more quickly. And again, you see the half-life equation. So this slide here summarizes everything we just talked about. Remember, differential is the most common, so this would be the first thing you should know. The one thing you have to pay attention to is the value of K, the rate constant. The units vary depending on the order. So you really need to study these here. For serial order, it's moles over liter times second. For first, it's seconds to the negative first. And for second, it's liter over moles per second. And then here you can see all the half-life equations. Reaction order must be determined experimentally. We cannot predict how fast a reaction will occur simply by looking at an equation. You have to actually get data, and you have to get a balanced equation. Remember that zero order has no effect on the rate. The concentration has no effect. First order, it's proportional. So if you double the concentration, the rate will double. For second order, it's proportional. So if you double the concentration, you will have 4 times the rate. In order to get the overall reaction order, you take the sum of the exponents for each reactant involved. So each reactant is going to have its own order. To get the total order, you add them together. So if we look here, the rate is K times the concentration of NH4 plus N times NO2 minus N. To get the overall order, you add this exponent here, N, and this exponent here, M. So there's a couple different ways we're going to go over how to determine the order of reaction. The first one I find the easiest. This is when you're given an equation and you're given data here. So it says, consider the following reaction between nitrogen dioxide and carbon monoxide, and it gives you an equation. It says the initial rate of the reaction was measured at several intervals. So what we have here is actual data from the experiment actually taking place. It says determine the order, write the rate law, and solve for K. So this is a classic problem you're going to have. And what you have to do to determine the order is figure out how does the concentration of this particular reactant change and how does that affect the order. So what you want to do with this, because you have two reactants, is you need to find a spot where one of the reactants is constant. So if we look right here, in this spot, the concentration of CO is the same, which means the only thing affecting the rate is the concentration of NO2. And if we look at this same spot, we see that NO2 is actually doubled. And what you're going to do is then you're going to see what effect does that have on the rate, which if we divide, it's about quadruple. So if doubling the concentration of NO2 quadruples the rate of the reaction, we know that NO2 is second order, because it's proportional. That is the definition. To get CO, now we have to find where NO2 is constant, which is going to be right here. So now NO2 has no effect on the rate, it's only CO. So here CO is doubled, and the rate stays relatively the same, which means the concentration change has no effect on the rate, which means it's going to be zero order. So if we were to write the rate law, knowing that it's NO2 is second order and CO is zero order, you'd write it here, K equals the concentration of NO2 squared times the concentration of C of 0. Because anything to the 0 power is 1, you can just completely eliminate CO, and you have a final rate law here. Then to calculate K, what you have to do is take this rate law, go back to your data, and plug in numbers. So these numbers here, 0.0021 and 0.1, just came from the data that I just looked at in the chart. And then I'm going to solve for K, and we're going to remember that it depends on the rate. So it's second order, so it's going to be molarity to the negative first times second to the negative first. Find the rate law expression using these following data. So if we look, we're actually going to have three things. There's three separate reactants. So again, we're going to look for spots where things are common or things are the same. So if we look for A, B and C, both in 2 and 3, are constant. Here A is doubled. A is cut in half. And the rate is about cut in half. So we're going to figure out, it says from experiments 2 and 3 right here, we're going to figure out that N equals 2, that the order is the second order. From experiments 1 and 3, so if we see here, same, we're going to figure out B is 0 order because there's no change in the rate. So even though this isn't doubled, we see it's still 2.4 times 10 to the negative 6. And then from experiments 1 and 4 here, same. These are both doubled, but only C affects the rate. So C is going to be a first order reaction. So the way you were going to write that is K times the concentration of A to the second, B to the 0, which you can eliminate, and C to the first. And then we're going to solve for K, and you should get 3 times 10 to the negative fourth. And remember, our unit is dependent upon the order of the reaction. Now, you can use, instead of second to the negative first, you can use minutes. That's fine. You just leave it as minutes. You don't have to convert that. It just means that if you were to solve for time from this, it would just mean the time you would get would be in minutes and not seconds. I'm going to have you go ahead and look at this problem and solve it on your own. The answers are down here. You should be that A should be first order and B should actually be third order, which is you're going to have to calculate. We're going to do this problem in class, but basically you set the two rate laws equal to each other. We will go over a problem like this in class. The Arrhenius equation is one of those things you might not need to know, but it's good to just have in your back pocket. You see here K is the constant, A is a frequency factor, E is talking about a calculation, and EA is the activation energy, and then RT is the normal RT that we're used to. Activation energy is the barrier or hump that must be surmounted for the reactants to be transformed into products. If you think about pushing a rock down a hill, you first have to push it up the hill to get it to go back down the other side. So the size of the hill would be the activation energy. The frequency factor is the number of times the reactants approach this barrier. And the activated complex is what happens after the thing is going over the hump. The activated complex is the top of the hill, quote unquote. It is when all atoms have been separated. So all the reactants have been separated, but they have not yet formed products. So if we look at the picture, you're always going to start with reactants and end with products being straight lines. Because once they are in their reactant form and they're in their product form, they do not change in energy. The activation energy is right here, the hill that has to be climbed to then go ahead and make products. And what a catalyst does, you can see right here, is it lowers the hill. So a catalyst works by lowering the activation energy, and that's how it speeds up a reaction. The transition state shown here, that's again, at this point, all the reactants have been separated, all the bonds have been broken, but none of the product bonds have been formed again. So this is kind of the very top of the hill. And again, the activation energy is this distance. One other thing shown in this graph is the energy change. So again, we don't really care. It's a state function. We don't care how high the activation energy is. All we care about is the difference between the products and the reactants. The frequency factor, again, is the number of times the reactants approach the activation barrier. The exponential factor is the fraction that approach and are successful of going out. Basically, it's how many reactants have the energy to kind of overcome the hump and slide down towards the product side. It increases with increasing temp, but decreases with increasing value of activation energy. So the more activation energy you need, the less particles are able to do to kind of climb over the hump. The collision model is exactly what it sounds like, how many particles are colliding per unit of time and how much energy those collisions are. A chemical reaction occurs after a sufficiently energetic collision. So you can't just collide two things, they have to collide with enough force to then go ahead and make products. The value of the frequency factor should simply be the number of collisions that occur per second. So we're looking at what we call a potential energy diagram. The initial energy you see represents the potential energy of the reactants, right here. It's going to be a straight line. The final energy is the energy of the products. The activated complex or the transition states up at the top. It's when everything's separated. And then remember, this is called activation energy. A catalyst would lower the hump. The overall energy change of the reaction is just the difference between the products and the reactants. To get the activation energy, you take the potential energy of the transition state, which would be here, the energy here, minus the potential energy of the reactants here. And the overall heat of the reaction is just the difference between the energy of the products and the reactants. If you have an endothermic reaction, the reactants have less potential energy, which means this is going to be below. And exothermic means the reactants have more, which is going to be above. So right here, this is showing an exothermic reaction. I'm going to go ahead and have you label this diagram. You're going to identify the reactants and products. So the reactants would be here, products would be here. The activation energy EA would be the difference between the reactants and products, so it would be the difference between here and here. Delta H would be the difference between the products and the reactants, and the transition state would be the very top. And then this diagram is actually going to be endothermic. If we go back, the reactants should have less potential energy than the products, which is what's happening here. Go ahead and answer these two questions. Using the potential energy profile, explain why the catalyzed pathway is faster. How do the reactants, products, and delta H energies change? And what effect will the catalyzed reaction have on the overall reaction, or the stoichiometry? So the answer to that should be that the catalyzed pathway is going to have a faster reaction rate because the activation energy is lower. It doesn't take as much time to kind of go over the hump. The reactant product and delta H energy should remain the same. And the catalyzed reaction will have no effect on the stoichiometry. The only thing the catalyst has effect on is the rate of the reaction. A reaction mechanism is a series of elementary steps for a reaction. You can kind of think of it like half reactions. It's a series of steps that occur during the course of a reaction. An intermediate is any species that is formed and then used. So you're actually going to see it on the product side and then on the reactant side. The elementary step is the reaction whose law can be written from its molecularity. Molecularity is just kind of how many molecules are reacting. So if it's unimolecular, there's one molecule. Bimolecular, there's two. Termolecular, there's three, etc. Series of elementary steps has two requirements. The sum of the steps must equal the overall balanced equation, and the mechanism must agree with the experimental rate law. The rate determining step is the slowest step, and the reason why that's very important is a reaction can only proceed as fast as its slowest step. So if you have one reactant breaking apart in 1 second and a product forming in 2 seconds, but the other reactant takes 5 minutes to break apart, your reaction is still going to take 5 minutes to occur. So that's the whole idea, that you're only as fast as your slowest step. So the rate determining step is always the slowest. So the way you're going to see that, I'm sorry, before we do that, the molecularity is here. Basically, you're just counting how many reactants you have, and that's going to tell you the coefficient, the exponent. So if you only have one reactant, it's just going to be a 1. 2 reactants is going to be a 2. You have 1A and 1B, 3 A's, etc. and so forth. It's pretty easy. So the way this is going to work is you're going to see something like this. You're going to be given 2 mechanisms, they're called. You're going to be asked for the overall reaction, and then you're going to be asked for the rate law. You're going to remember that the rate is only as fast as the slowest step. We're going to go ahead and do this together in class, but if you look, basically, if you see here the NO3 are intermediates because it's made and consumed, so you'd cross that out. And then you'd go ahead and cross out the NO2, one of them, not both, just one, because that's, again, an intermediate. And then we're going to do the rest of it in class. Again, this is another reaction where we're gonna do the sample problem in class. This kind of is a backwards way of doing it. It's giving you proposed steps, and you have to figure out which one's the rate determining step and show that it is consistent with the rate law. We are going to do that one in class as well. A little bit about catalysts. A catalyst is the thing that speeds up the reaction, and they're really, really important in the body. They do a lot of things with your digestion, with other reactions that take place in your body. So for example, you're going to have a catalyst in all of your saliva has a bunch of catalysts to start to break down your food. You're going to have an active site substrate that fit like a lock and key. So you're going to go ahead and read this. This is a section in your textbook. It's going to really understand catalysts and how they work in the body.